So we start with L'Hopital's rule. Notice the spelling of that is L, kind of like here is hospital, right? But it's called L'Hopital's. At that time, I actually make an animation for you guys. It says that if you have the limit of the quotient of two functions, and if it's of one of these two emergency type, and then you have to rush them and to hospital and apply L'Hopital's rule. In order to apply L'Hopital's rule, the function f and g has to be differentiable. Okay, so and the quotient over here of f over g, as this x approaching to a, has to be of one of these two emergency type in order to go directly to the hospital. So over here is this two emergency type right here. 0 over 0 or infinity over infinity. If it's not of these two emergency type, you don't go directly to the hospital. You had to do some, maybe sometime do some CPR first, okay? Or maybe do some other things first before you apply L'Hopital's rule. So these two types are the one that you can apply L'Hopital's rule directly. Those are the two emergency types. The L'Hopital's rule says that the limit of this quotient, if it's of one of these two emergency types, 0 over 0 or infinity over infinity, is the limit of what? Can someone tell me? What does the L'Hopital's rule says? It's the limit of also a quotient, but it's a quotient of what?
F prime over G prime?
Yes, you got it. So it is the limit of F prime over G prime. So right here, you can differentiate the function in the numerator and differentiate the function in the denominator. And this quotient has the same limit as this. And that's what L'Hopital's rule says, if it's one of these two types. Okay. So in order to differentiate the function here, f and g have to be differentiable. Okay, so to do that. Now, there are a couple notes over here. Even though here says that, so you have to check, okay, first note here, you have to check if the limit is of this two type. Okay. Number two, you have to, number two here, x approaching to a can also be replaced by x approaching to a from the left, from the right, x go to infinity or negative infinity. Okay, so the L'Hopital's rule also apply. Okay, all right. So there are a couple notes here. You can see that. Now, we also talk about indeterminate product, okay, of this type 0 times infinity. This one here, limit of this type, you cannot apply L'Hopital's rule right away because it's not this, right? So it's not yet to be this. So you need to convert limit of this type into either this type or this type. So what kind of trick you can convert this into this type and this type? So say f times g, and then what do you do? Remember we talked about we did some CPR, right? Do you remember what kind of CPR you did?
You take the reciprocal of 1?
Yes, take the reciprocal 1, okay? So you're going to keep one of them in the numerator and then divide by the reciprocal of the other one. So same with this one. Usually you keep the difficult function on top, okay? And then it's easier, okay? You can decide which one to keep in the numerator. And by doing this, you can convert this type into one of the two emergency type. And if you can convert into that, then you can apply L'Hopital's rule. So here, you need to do some CPR to get to this. And then after that, then you can apply L'Hopital's rule. Now, also, if you have an indeterminate difference of this type, infinity minus infinity, that's not the emergency type that we have. It's not this one, right? So what can you do to convert a limit of this type, infinity minus infinity, into these two emergency type? There are three ways to do it. Okay, 1, 2, 3. Can you guys remember? Can you guys name some of them? Number 1, you can take out a common factor. When you take out a common factor, actually, okay, take out common factor is like this one. Okay, you can take out common factor. When you take out common factor, actually it gets to the type 0 times infinity. So it's in the factor form. Then after that, then you do some CPR. Okay, you keep one of them. You keep F. Say you keep F on top, and then divide by the reciprocal G. Okay, so that's CPR, and then you were able to convert that into these two emergency type. When you take out common factor, it's in the product form, and then use the CPR trick that we talk about, can convert to that. Another way to convert this type into this eventually is to use a common denominator. Okay, and then what's another one here? Do you guys remember? Oh, what? Rationalizing. So suppose this one over here has, say, a radical, subtract a radical, then what do? We will, what does rationalizing mean? So you're going to multiply this by that radical adding a radical. So they are conjugate. Okay, so these two are conjugate. So multiply by the conjugate, but when you multiply them, you also divide by it. Okay, divide by that. So you're going to rationalize it by multiply the conjugate of this up and down. Okay, then you're able to convert that. You might be able to convert this type into either this one or this type. Okay, let me do that. Okay, so that was the trick to do this indeterminate difference. So you can use 1, 2, 3 ways to do it. Okay, so those are some way that you can do it. And for 4.4, we also talk about indeterminate power, 0 to the 0, infinity, or to the 0, 1 to the infinity. Those are the three indeterminate power. Okay, the three type. Then to deal with this kind of limit of the three type, what did we do? Do you guys remember?
You take the limit of the ln?
Yes, very good. So because the base here it's a function of x, right? Okay. Oh, here this is a typo. This is limit of this. Okay. The limit of this, you see the base here, it's a function of x. The exponent also a function of x. So when both this and this are function of x, as x approaching the a, that all changing, then what to do here is you want to bring down this exponent. To bring down the exponent, you can let y to be this whole, you can take ln of this, okay? Take ln of that. So when you take ln of that, what's ln of y here? What is it equal to?
G of x.
G of x times ln of f of x, right? Okay. So you will have g of x times ln of this f of x. Then that way we can find the limit of ln of y. And then at the end, once you find the limit of ln of y, you can find the limit of y by suppose the limit of ln of y, for example. So example, suppose the limit as x proportional to a, Ln of y is say equal to say 3. Suppose. Then we can try to go back. We can go back and find the limit of y. Okay, y is the one that we're looking for. This y over here. Okay, we want that y to be this. Right, this is the y. Okay. Then the limit y is going to be equal to e to this power. Because Ln of y go to 3, y is going to e to the power. Okay, so once you can find this limit, you can find the limit of this quantity that you were looking for limit, that one. Okay. Okay, great. So that's how we deal with indeterminate power. Okay, indeterminate power of this 3 type over here. And then after that, we went to chapter 6. For chapter 6, we start with area between curves. So say we're trying to find the area bounded by this curve above and this curve below. What's the area? What's the area formula? The formula for this is this. Is the integral of this y on top, subtract this y at the bottom, y on top, subtract the y at the bottom. That corresponds to actually the height of this rectangle. And then dx here is something like the delta x. If you think about that as the area of the small rectangle, and then you use integral to sum up all those rectangles, and the more rectangle with equal width that you got, then the sum of those rectangles approaching to the area between the 2 curves, right? Okay, so integrating all those and add up all those small rectangles. Think about that integration as adding up all those small rectangles. So each rectangle is yt minus yb multiplied with delta x. So this is this one right here. And then integrating them. Okay, so sum them up. X here go from A to B. You get the area between these 2 curves. So it's y on top, subtract y at the bottom. Okay, right? Which makes sense if you think about if f and g are positive function, right? It makes sense. It's the area under the f, subtract the area under the g, right? You get this area between the 2 curves. Now, suppose sometimes the curve look like this. Okay, think about like this way. Sometimes the graph of the function f is like this. The graph of the function g is the blue one right here. They cross each other. It's not always one above the other, right? Okay. All right, that was really loud. That was. Okay, so at that time, if you try to find the area between the 2 curves, you had to actually break it. You want to break it into, consider that piece by piece. So here from A to C, then the pink one on top and the blue one down here. This from C to D, the blue one on top, this one down here, etc. Then the area between the 2 curves is the integral of the absolute value of the difference of the 2 functions, f minus g. And to break this one, and then you break this one here into the sum of the integral. So for example, this one here, you will from A to C, then you will have the function on top is the g. Okay, so then you will have g minus f, and then plus here you will have from C to D, then you have g minus f, And then from D to B, then you will have F minus G. So you break them up this way. Notice that this absolute value over here, you can, when F is greater than equal to G, it's just F minus G. When G is greater than equal to F, then it's the opposite.
Is the first one fx minus qx?
Oh, yes. Now I can see better when it's big. Yes, you got it, okay? The first one here is f of x minus g of x. You got it. Good job. You pay attention, okay? The f over here, yeah, this is a f, and this is g. Okay, good job. Okay, now that was when the curve is one above, one below, right? Or when they go up and down, sometimes cross over like that. What about the two curves are like this? Say one on the left, one on the right. Then what will be the area between the two curves when y go from C to D? So what should I put over here?
Y minus G of Y?
Yes, very good. So you use you use the x coordinate on the right, subtract the x coordinate on the left. Okay, so the one on the right is f of y. The x coordinate here on the left is g of y. So you use fy, subtract g of y. That will give you the length of this rectangle, and then you times delta y, give you the area of one of this rectangle. Okay, so that is fy minus g of y dy. Y go from C to D. So to sum up all those rectangles, you got the total area A. All right. Now for this one, so another way to write this is x coordinate on the right, subtract the x coordinate on the left, and then dy. So this formula is x on the right, subtract x on the left, dy. Think about it as the area of one small rectangle, like this one. And then you sum them up using integration. Y go from C to D. That's the area between the two curves when y go from C to D. Okay, and over here I gave one example to you, so you can take a better look when you have time. Okay, next we talk about volumes. So for solid, we can actually cut them up in calculus. We love to chop things up. We chop things up into very small pieces, and then we use integration to add them up. Okay, so to find the volume over here, for example, a solid like this, we're going to slice it into thin slice, and then you just take one particular slice and try to find the value of that slice, and then you use integration to sum up the value for all those slices, and let the number slice go to, and then let the slice here be thinner and thinner, and then take the limit of that. If you divide that into n slice here, and if you chop it into more and more small slice, then the limit of the sum of those slices will be approaching to the value for this whole solid right there. So the value for that is, well, if you look at this particular slice here, it's almost like a cylinder. But when I talk about cylinder in here, in calculus right here, the cylinder we talk about, they all have the same cross section. Okay, so think about it's like it seems like they all have the same cross section for this one right here. Okay, so the cross section over here is a of x. Okay, for every different x, when you move the x, you see the cross section here change. Sometimes cross-section like that, sometimes cross-section like that. Okay, so this cross-section area is a function of x. So that's why I call A of x. As x change, this cross-section area here change. And the cross-section here, area here, times dx, think about that as a delta x, that will give you the value for one of the slices here. And then use integration to sum them up, and you get the total value over here. So that's the idea. This is the idea of the formula using cross-section. So the value is equal to the integral of the cross-section area dx, and the area here has to express in terms of x. It's a function of x. Okay, we're integrating with respect to x. So this has to be a function of x. Okay, x go from a to b, so x go from here a to this b. Then integral of the cross-section, okay, and then dx, x go from a to b, give you the total value of the solid. Okay. Similar, if you slice it, right? If the solid is actually, if you turn this one up and down like that, instead of left and right, you can actually, you still do the same kind of slice, right? But this time the value is going to be the integral of, with respect to y, so dy. Then the cross-section here has to be expressed in terms of y. So this cross-section area has to be expressed in terms of y. And then think about this as the value for one slice, and then you use integration to add them up. So y go from c to d. So you can try to imagine maybe you have a solid like this, right? And then you slice it. So suppose you take the slice right here. This is this one, the area of that. And then dy over here is, the dy is that one right there. Okay, dy. And then you sum them up. Y go from c to d. So y here go from c and then to d. Okay. Now, for the cross-section, when the cross-section is a disk, then the cross-section area, okay, that one right there, this cross-section area over here, then it's going to be pi r squared. Okay, pi r squared when it's just a disk. Now, what happens if the cross-section is a washer like this? What will be this cross-section area? So that will be pi times what square minus pi times what square? Pi times the outer radius. Huh? Yes.
Oh yeah, the outer radius.
The outer radius? Yeah, outer radius. From here, the axis to the outer side of this, right? So outer radius square minus pi times the inner radius square. That will give you the cross-section area right there. Okay, so this is using cross-section. Sometimes the cross-section is not circle or is not a disc or washer, and that still apply. Okay. So for example, the cross-section could be a triangle, like in this case. See, each cross-section, if you slice it, okay, perpendicular to the x-axis, then each cross-section here is going to be a triangle. It's going to be a triangle, okay? And you would just find the cross-section area of this one triangle, and then times dx, because this is perpendicular to x-axis. And then x go from whatever a to b, okay, to find the total value. Sometimes cross-section could be a circle. Then you can just use pi r square right? Semicircle, you have 1/2 pi r squared. And if it's square here, suppose this is x. Suppose this is, say, whatever here is x, whatever. Then you have pi times the size, not pi. It's just the side, square the side to get the area. Rectangle is the length times height, etc. Okay, so this is the finding volume using cross-section area. Depends on what the cross-section here is. Okay, you can find the corresponding cross-section area. Depends on the shape of the cross-section. Okay. All right. So, okay, 6.3. We talk about finding volumes using the shell method. Okay, so we first have a shell, and then we actually got the formula for the volume for a very thin shell right here. Okay, see the value for this. Okay, think about the shell over here. The R here, so R1 is the inner radius. R2 is the outer radius. What is this R? This R over here is this one here is in the middle. Okay, this in the middle. It's the middle of the shell. Okay, so it's actually between the outer and the inner radius. So which means you're going to take the average of the outer and inner radius. So think about this R here as the R from the center to the middle of the shell right here. Okay, and we got the volume is equal to the value for this one shell. Okay, so think about this shell over here. This shell over here is 2 pi r. Okay, remember last time we talked about how we try to remember that. So you think about you use a pair of scissors and cut open the edge and open that up. So it's going to be 2 pi times that r, 2 pi r, times the height of that. The height of that is h. Okay, let's call it h. And times the thickness of the shell, delta r. Okay. Then you get the value for that shell. So when you open it up, it's kind of like a thin rectangular box, right? Okay. So that was the idea for the shell method. So the value for that is circumference times height times thickness. Circumference here is 2 pi r, 2 pi r right here. That's the circumference. The height of that is h. And the thickness of the shell is this delta r. So 2 pi r times height times thickness is the value for this one shell. Okay. And then we use this. Okay. So that's the formula right here. So, and then we can, when we try to find the value, for example, if we try to find the value by rotating this region about this vertical line over here, so you can draw the solid like this. Okay. We draw the solid. Then if you use a shell method, then you will draw a nice segment that is parallel to this axis that you rotate about. Okay. So you're going to draw this. Okay. Here is the picture right here. So you draw a rectangle or a very, okay, you can just draw a nice segment and imagine that as a very thin rectangle that is parallel to the axis that you rotate about. And imagine that this is going to rotate and you get a thin shell. Okay, notice that is parallel to the axis that you rotate about. Okay. Now, on the other hand, if you use the disc or washer method, then when you rotate this region about this axis, you're going to draw a nice segment. Imagine that as a very thin rectangle. When you rotate about this axis, it turns into a disc or washer. Okay, so that's the washer. And notice that this segment is perpendicular to the axis you rotate about. So the difference between the shell method, okay, so this one here is the shell method, and this one over here is the washer method. Okay, so this one parallel to the axis you rotate about. This you will be perpendicular to the axis that you rotate about. That turn into, when you rotate, that turn into a thin shell. When you rotate this, that turn into a washer right here, or a disc. Okay, so remember that. And now if you try to find the value of the solid when you use the shell method, then we'll use this formula. So each shell is going to be if it's like this, the circumference, which is 2 pi x, times the height, in this case is f of x, times the thickness of that. The thickness of the shell is delta x. So that you can think about that as the value for one shell, one thin shell. And then we use integration to sum up all those shells. The x go from, say, A to B. Okay. For example, in this case, the x here go from 0 all the way to 2. Okay. See, the x start from here and then end at 2 over here. X go from 0 to 2. Then you will get the total value for the solid right here. Okay. So that was the shell method. And the difference between the shell method and the washer method. So you can compare them side by side. For 6.4, we talk about work. And the work that we talk about here will be a force that is not a constant. Instead, it is a continuous function. If you want to find the work done by this function along a straight line from point A to point B, then the work done by that force is going to be the integral of that force. X go from A to B. So that's the integral of that force function with respect to x. X go from A to B. So that's the work. Okay. So remember, that's the work. Okay, work done. By moving this particle from here to here, how much work is done? So we integrate this function with respect to x. X go from A to B. That's the work done. 6.5, we talk about average value of a function. So look at this picture over here. We have a continuous function. So it looks like this is the average. Okay. What does it mean average? Well, if this is a positive function, right? So if you take that average, the part that above this, you can cut it and then you fit in here. And you should get a rectangle. The area of this rectangle is actually equal to the area under the curve from A to B. So the average value of the function from when x go from A to B, that is a formula. So that will be equal to the area under the curve, this gray area, or this pink area, and then divide by the width for this, the width of this interval from A to B. So area divided by the width give you the average height, right? And the average height there is the average value of the function. So the formula is the area of this one is the integral from A to B. Okay, think about the pink one right here. Divide by the width is B minus A. Then you get the average value of the function. Then we're done with chapter 6, and then we move on to chapter 7. I wonder how much time. Okay, let's try our best. So we talk about integration by part. So first we review the product rule, right? When you differentiate the product of the two functions, that's equal to f prime times g plus f times g prime. Then integration, and this is the differentiation, and the corresponding integration rule is actually the integration by part. Okay, so this rule in differentiation corresponds to this rule in integration, which is this rule here is called the integration by part. Anybody remember integration by part formula? Okay, let's maybe just think about this. The integral of u dv is equal to what? Everyone? uv, right? Minus the integral of what?
VDU.
vdu. Yes, you got it. Okay. So if you use this notation, so that will be f of x, g of x minus integral gx f prime x dx. Okay. So these two are the two corresponding rule. This is integration. This is integration. Okay, this is differentiation. So integration by part and the product rule actually are the two corresponding rule. One in integration, one in differentiation. And I gave one example over here, y under, okay, and I gave you some hint to some kind of remark right here, how to sometimes what to do. Sometimes you need to do integration by part twice. When you have this form, e to the x times sin x, okay, when you integrate that, sometimes you need to do it by part twice. And then you have to, after that, you get back to the same integral that you start with. Then you can regard that integral as a variable. You can solve for it. So you get 2 of this equal to that, and then you can solve for that by divide this by 2. Okay. So that's some remark that you might want to sit down and take a look at that one. And I also went over the trick, how to choose u. So you want to choose u so that the duality of u is simpler, or at least not more complicated. Okay, right here. And a lot of time you can try to use the Ni8. Okay, it's not Nia. Okay, Ni8. Okay, the Ni8 rule. Okay, you can choose the u going down this priority. So you can choose, if you have log function, you would let u equal to that first. And then if you don't have that, you can try to see if you have inverse trig, algebraic trig, or exponential, and you try to let u to be that. So for example, so if you have log function and inverse trig function, you let u to be that log function, because this one has higher priority, right? Okay. So that is some suggestion. It doesn't work 100% of the time, but that is going to work a lot of time. So try to remember that one. Okay. And I have some remark of how many times if you have this form, sometimes you need to do integration by part twice. Okay. And whenever you see, if you see an integral, if it's in the form of x to some power times a transcendental function like e to the x, ln of x, a trig, inverse trig, then you should consider using by part. Okay, so that's a big hint that you will do the integral by part for that. Okay. Okay, for 7.2, we evaluate integral of 2 types. Actually, maybe more. So first, we talk about integral of, say, sin x times cosine x, where the exponent on sin x, cosine x, maybe one of them is odd. Okay, then you try to think about this trig identity. You will try to make the power on either side, the one that, if it's the one that has odd power, you want to save one factor of that. So, for example, here cosine of x, the cosine here has an odd power. You want to save one factor one copy of this cosine x. So cosine x together with the dx. Then the remaining cosine of x here, you have an even power. Then that we can use this trig identity to express that in terms of sine x. And what happened to this cosine x that you save together with dx? That is going to change into d of sine x. So which means that if you let u to be sine x, that is going to become du. Okay, so that's the trick. So whenever focus on the one that has odd exponent, okay, you have sine x times cosine x. If you see the one that has odd exponent, you will save one copy of it together with dx. Like this one, sine x has odd exponent, you save that. Take one copy of this sine x, save it with dx. Okay, and then later use a trig identity here, and then here this become negative du if you let u to be cosine x. So everything after, if this u equal cosine x here, then you will want to express this function that you integrate with all in terms of cosine x. So this is in cosine x, though nothing to change. Then this is not in cosine x, use this identity to express in terms of cosine x. If the exponent on sine x and cosine x are both odd, then you can use either strategy. You can either save a cosine x, you save a sine x. If both of them are even, then we use the half angle formula, okay, to do that. This one we're going to use a lot in calculus 3. So remember this formula, okay? And this is also the formula, this double angle formula for sine of 2x. You also might want to review some of the trig identity before you move on to calculus 3. Okay, and then we also talk about what happens if the function we integrate with is in the form of tangent times secant, tangent x times secant x. And the exponent on tangent and secant, there are two cases. When the exponent on secant x here is even and greater than or equal to, you want to save a secant square x together with dx, because that is going to change into, if you let u to be tangent x, that is going to change into du. Okay, and then after that, because u is tangent x, you want this to be in terms of tangent x using this trig identity over here. Then they will be all in terms of tangent x, tangent x, tangent x. Okay, so that u equal that, this is du, and this will be all in terms of u at the end. Then, so the trick to remember that is also think about this trig identity. When you see this type of integral, tangent times secant, think about this trig identity. Notice the exponent on tangent and secant are even. If the exponent on tangent here is odd, then you want to save a tangent x together with dx, so then the remaining exponent on tangent will be even, so you can use this identity. However, just saving one tangent x is not enough, because that we don't see a d of what equal to that. So the tangent x needs to save a friend together with it, which is a secant x. Secant x tangent x is the derivative of secant x. So if you let u to be secant x, this is just du. Okay, and then later you expect everything in terms of secant x, then everything will be in terms of u. Okay, so that was a safe method. I call it safe method. You save one factor of this secant x tangent x like that. Okay. This is a formula. Okay, this is a formula for antiderivative tangent x, antiderivative secant x. It's kind of worth remember. I put down two different forms. These two forms are actually equivalent. I like this one better because I see secant and tangent, they always go hand in hand, and that will make me feel very that actually help me remember. And besides, it doesn't have the negative sign like this one. But some other in your high school or in some other instructors, sometimes they use that, but they're equivalent. The reason is over here. Okay, and then the strategy to integrate sine times cosine when the angle here are not the same. Then we'll think about using this trig identity right here. Okay, depends on what this two is. Okay, if it's sine cosine or sine sine or cosine cosine, you will think about which one to use. Okay, so use those product identity. 7.3, we talk about trig sub. Okay, trig sub is when you use when you integrate function of the square root of either a squared minus x squared, a squared plus x squared minus a squared. One of these three forms. When the integrand involve this, think about the trig sub. Sometimes they call it data sub. So you net x equal to what? Okay, so there's some. The way that I remember is I will try to think about this a squared correspond to the 1. And we think about 1 minus what squared equal to what squared. Because you want to have a perfect square inside the square root. So 1 minus, we know that 1 minus sine square is cosine square. So we let x equal to a, because this is a sine theta. Okay. Then after the trig, then this part, this whole square root will turn into a cosine theta, like that. Similar for this 3. Okay. When you do trig sub or data sub, don't forget at the end, you want to return from data to x by this right triangle trig. So if, say, for example, x equal to 3 sine theta, then you will draw a right triangle, put the data here. Then sine theta will be x over 3. So put x here and 3 here. You can figure out the remaining side by the Pythagorean theorem. And from this right triangle, you can figure out cosine, secant, tangent, whatever that whatever that you got when you do the trig sub, you can use this right triangle to return from data back to x. Okay. So here data will be inverse sine of x over 3 also. Okay. So for example, you can the cotangent data you can read from this diagram, and then the data here will be equal to inverse sine of x over 3. Okay. So we turn from data back to x, use the right triangle trig. And then I also gave more example. Okay. Right here, you can take a look. 7.4, we talk about integration of rational function by partial fraction decomposition. Okay, so we call that PFD, right? PFD, partial fraction decomposition. And here are the steps to do it. First, we look at the rational function. We check the degree. If the degree up here, for example, like this one, you see the degree up here is degree 2, down here is degree 1. This one has higher degree than this in the denominator. So you use long division first. That's the first thing to do. Okay. Even when they have the same degree, when the degree are equal, you still use long division first. And then for the remainder over divisor part right here, you can decompose it using partial fraction decomposition. Okay. And I put out this 4 cases, how to decompose them, okay, for different cases. And I also have example how to find those A and B right there. So here's example. Okay. So you can take a look. Okay. For 7.5, strategy for integration. So the table of integration formula, we have this 20 formula. Out of this 20, this 2 you don't need to remember. The hyperbolic sine, hyperbolic cosine. If it ever come up, you can always look it up. Actually, it's not that hard to remember, but you're not responsible for it. the star over here, this 2, you don't really need to remember. But this 2, you want to remember, 17, 18, okay? And then I have this 4-step strategy right here. So first, you will look for obvious substitution. See if we can do U sub, okay? So can I do a U sub? Okay. So can I do an obvious U sub? If you can, then go ahead, okay? Because U sub is actually the most simple method. And then later, you're going to classify the integram according to the form, okay? And then and then you can try see if you can do integration by part. And if it's one of this square root of x squared plus a squared, etc., you think about trig sub or data sub, right? So if it's like that, you think about trig sub, which is also called data sub. Okay, if we involve this, right? Okay. Okay, and here is the method, okay? And then integration by part, if you see those patterns that I told you before, okay? And number 4 is try it again. Okay. Sometimes you have to use 2 different methods, not just one method. So maybe you have to do a U sub first, and then later you do an integration by part. Okay, so you have to combine different methods sometimes. Okay, and then 7.8, we talk about improper integral. For improper integral over here, there are 2 types, okay? Can someone tell me what's the first type? Do you guys remember? I'm gonna ask someone. How about dead end? What's the first type of improper integral? Are you guys here?
When one of the endpoints is infinity.
Yes, you got it. Good job. Okay, so one of the limit of integration here involve infinity or negative infinity. That's the first type of improper integral. Then the way that you do it is you can express that, replace that infinity or negative infinity by t, and let t go to that. Okay, so in this case here, t go to infinity. So it's the limit of this proper integral. So when t here is a real number, right? So this is a proper integral. This is an improper integral. This improper integral is the limit of this all those proper integral as t go to infinity. Okay, providing that this integral here exists for every t greater than or equal to this a. Okay, if the limit exists, we say that integral is convergent. If the limit does not exist, we say that integral is divergent. Well, if upper and lower limit involve both infinity and negative infinity, you can break it into 2 parts. Okay, so you can break it into from negative infinity to a, and then a to infinity, break into the sum of these 2 integrals. Usually it's 0 if 0 is in the domain for the function. Okay, and when you do that, if you find one of the integral, for example, say this one here, this integral here diverge, you don't even need to think about the other one. If one of this diverge, then this one here will diverge. So in other words, this one converge, providing that both this and this converge, which means both this one and this one equal to a finite number. Okay, so there's no canceling out like this. Say this is go to negative infinity, this go to positive infinity, then we still say this one here diverge. Okay, there's no they're not going to cancel like that. Okay, it's not going to cancel become 0. So we still say this integral here diverge if you get this case. Okay, and then we talk about P integral. This is actually an improper integral of type 1. Okay, you have infinity here as the limit of integration, upper limit of integration. This one converges to, wow, once you know this trick, you can see right away. It converges 1 over P minus 1. So for example, if you have integral 1 to infinity 1 over x to the 5th power, and what does it equal to according to this? This is what? 1 over 5 minus 1. Yeah, it's 1 over 4. So you know this integral right away. It's 1/4. Some people say, wow, how did you know that? You look like a calc. Similarly, you have some magic, right? Yeah, because that's a pre-integral. Okay, so you know that. Okay, so P integral here converge if and only if the P here is greater than 1. And that actually reminds us of the P series, right? Do you guys remember later on we learned about the P series? 1 over n to the P power. This is a P series, right? And it converges if and only if what? P is greater than 1, okay? So similar. So this P integral converge if and only if P is greater than 1. This P series converge if and only if P is greater than 1. Okay. The second type of improper integral will be it's not that obvious. It's kind of hidden. Okay. When you have infinite discontinuity at maybe one of the end, like this end or this end, or maybe in the middle. So there is an improper integral of type 2. For example, here's an example. 1 over, okay, what is that function? 1 over x minus 1. The graph for this is going to be, so it's going to be like that. This is the graph of 1 over x minus 1. It is undefined when x equal to 1. You see that you have a infinite discontinuity over here. So this integral from 0 to 3, here is 0, here is 3, 0 here, and 3 over here, will correspond to this right here. That is an improper integral. We have infinite discontinuity between 0 and 3. So it's improper. Okay, it's kind of not that obvious. So the way that we do it is we need to break it into the sum of two integrals. The first one go from 0 to 1. The second one go from 1 to 3. Okay. From 0 to 1 over here, it turned out to be neg infinity. So here we got that is neg infinity, that integral. Then you don't need to find the other one. You can say the integral here diverge because it's the sum of this one and that one. If this one diverge, one of them diverge, then this whole thing diverge. Okay, so it's divergent for that one. Okay, you don't need to evaluate this. Okay, and then we go to chapter 8. For chapter 8, we talk about arc length. So the easy way to remember the arc length formula is this. It's the integral of the differential arc length. Where this differential arc length ds over here, you can be written this way. If you have dx outside here, this is dy dx. If you have dy outside here, you have dx dy over here. Now, when do you use this? When do you use this? You use this one when y is a function of x. You use this one here when you can y x as a function of y. Okay, so it depends which one. Sometimes you can use either one, both of them work. Then you can just find the one that is easy for you to do the calculation. Okay, so that's when do you use that and that. Okay, and then we talk about arc length function. Okay, 8.2, we talk about area of surface of revolution. We first got the formula for any of those surface revolution. It's going to be 2 pi r times L. What is the r there? This r here is the radius of the surface in the middle. Okay, see here in the middle of this tube. This is r here. In the middle of this cone, this is r there. In the middle of this, how do you call it? What kind of shape do you guys call this? A cone with the top off. Okay, you chop off the top of the cone. Okay, this r here is in the middle. Okay, in the middle of this r and this r. Basically, this is the average of this r and this r here. Okay, so we actually got the formula. It's going to be 2 pi r. Okay, this r right here in the middle times L. The L is this from here to here. Now, once we got that, we had used that, actually got the surface area formula. When you rotate an arc about this x-axis, then the surface area is it's going to be, well, the way that you do that, you pick a point, okay? Why this point? Pick a point on the arc, okay? And label that x comma y. And if it's rotate about this x-axis, then you would draw a circle, rotate about this x-axis. Then the circumference of the circle is 2 pi r, which is, in this case, r is y, so 2 pi y. And then, see, the 2 pi r right here, right? The 2 pi r, so that's 2 pi y in this case. And then what is the L? The L is the differential of arc length. Okay, think about this is the L, this is the L, this is the L. The L is here, think it's the differential arc length right there. The ds right there. Okay. Now if it's rotate about the y-axis, then this point x comma y going to trace our circle. The circumference of that is going to be 2 pi x because x is a radius. And then ds here. The ds here is the differential arc length. You can either use this one or this one. Depends if y, so if y is could be written as a function x, you can use this one. If x could be written as a function y, you use this one. And then you will get the corresponding formula for the surface area of revolution. Okay, and then we went to chapter 10. Wow, that's a lot. Okay, and then we talk about parametric equation. Okay. So you can parameterize x and y, express them as a function of a variable that's called a t. And here is a pair of parametric equation for a circle. If a circle have the center hk and radius r, then a pair of parametric equation for that circle is this one. Okay, this is one way to parameterize this circle. And then we talk about cycloid. This is the parametric equation for cycloid. Okay, having data as the variable. Okay. And then we talk about calculus with parametric curve. Okay, first derivative and then second derivative. First derivative tell you increasing, decreasing. Second derivative tell you the concavity. And then we talk about area under parametric curve. Okay, so those are the formula here. And then the arc length, when you use parametric equation, then the ds over here is going to be that right here. So I actually put them together. So the differential arc length, if y is a function x, you use that. If x is a function y, you use that. If x and y are function of t, you use that. Okay, so depends which one is. So the ds here will use a corresponding one. Okay, this part over here is still the circumference of circle when you rotate about the axis you rotate about. Okay, okay. And then 10.3 is polar coordinate. You're going to use this in Calc 3. So you better review this before you go on to Calc 3. So polar coordinate, the way that we use it, you need to remember this. X equal to r cosine theta. Remember this one. The x here is r times cosine theta. The y here is r times sine theta. Okay, and then you should also remember this one. Okay, because you're going to use it again in Calc 3. Okay, r squared is x squared plus y squared. Tangent theta is y over x. So remember that. And here's some way to tell the symmetry over here. And here are some common polar curve. You don't need to memorize it, but it's interesting to look at, isn't it? Okay. And then calculus in polar coordinate. You actually have something like this in Calc 3. So to find the area between these two polar curve, Okay, so it's going to be 1/2 this outer R square minus the inner R square d theta. Theta go from alpha to beta. We first talk about what's the area of a sector of a circle. It's 1/2 R squared theta. Well, think about this as like a triangle. So 1/2 base times the height, 1/2 times R theta times R, is 1/2 R squared theta. So that's one way to maybe help you to remember the area of that. So if you have a polar curve, R is a function of theta. So the R over here, okay, think about them, you divide that into sectors, and each sector is going to be almost like a part of a circle with radius R. Okay, then this is kind of area of one sector, and then you integrate that. Theta go from A to B, you get this area. So think about this right here, and as the data increase, it's going to sweep out this area right here. So that's the formula for that. So you use it again later in Calc 3. And then the area between these two will be this formula right here. Corner intersection, you can solve it. And a lot of time you use some graphing device or calculator. And here for the arc length. So for the arc length, the ds, if you use polar curve, then the ds can be expressed this way. Well, you can actually, this one, you're not responsible to remember, okay, but it's good to know, like it, okay. And then we talk about tangent to polar curve, okay. And then we go to chapter 11. Chapter 11, we talk about the strategy for testing series. We learn about test for divergence, which is also called the end-to-end test. That's the easiest one to use. If an doesn't go to 0, then the series diverge. And then we talk about geometric series tests. Okay, so geometric series converge if and only if the absolute value of R is less than 1. And we actually know what does it convert to if it converts. It converts to first term over 1 minus R. And then we have the P series test. It converges if and only if P is greater than 1. Okay, and then we have the telescoping series. Okay, and then we have the integral test. For integral test, you have to check the relating function is continuous, positive, or negative alternately. Okay. And then you will also find the corresponding integral from n to infinity. And if that integral converge, then the series converge. If that integral diverge, then the series diverge. So they come together, then die together. Okay. And one example using the integral test is this series right here. And for number 5 is the comparison test. We have 2 comparison tests. One is the direct comparison test. One is the limit comparison test. The direct comparison test, you have to show that, okay, both of them require the term had to be greater than or equal to 0. They have to be positive term. And then this one here, you have to show that Bn greater than or equal to An. But this one you don't. Okay, you look at the ratio An over Bn. If it's equal to a positive constant, okay, the C over here is a positive constant. Okay, positive constant. Then both the series over here will be both converge or both diverge. So they converge together or they diverge together. Okay. All right. And then for the direct comparison test, if the bigger positive series converge, then the smaller positive series converge. If the smaller positive series diverge, then the bigger positive series will diverge. So that was the direct comparison test. Now, when do you use it? Which one to use? I like to use the limit comparison test because for me, it's easier to take the limit of that. Okay. And usually when the series is kind of like, sometimes it's not easy to see which one's bigger. Then you would like to do the limit comparison test. Then when you do the comparison test, you should take the dominating term of the numerator and denominator. So here you take 2n, you take 2n squared, and then you take square root of n squared. Okay, so, and then you're going to compare this with this series here. So you look at the dominating term. You can put a 2 here if you want, but you have a constant like that. Okay. Okay, and then next one we talk about the ratio test. The ratio test, we just talked about it. When the an involve the factorial or a constant to the n power, you use ratio test. So that's a hint that you use ratio test. Actually, ratio test is very easy to use. So maybe a lot of the time you should try this one before integral test. Okay. All right. Now, the ratio test doesn't work when the limit of this ratio, the absolute value of the ratio is equal to 1, then you have to use other tests. So do not use the ratio test when the series is kind of compatible to a p-series. Like this one is compatible to a p-series. Then you don't want to use ratio test on that. The root test is very similar to the ratio test. Okay, the result is very similar. Okay, so, and then we also learn about the alternating series test. Okay, the alternating series test. Okay, first of all, you have the sign has to be alternate, and this part has to be always positive. What are the 2 conditions to check? Can I ask you guys? Bn what? Number 1, what do you check? B.
It must be decreasing?
Yeah. Actually, you want to check if Bn go to 0 or not. That way it's easier to check. Okay. So we want to check if Bn go to 0 or not. If not, then you can actually say that the series diverge by test for divergence. Okay. And if Bn go to 0, then we also check Bn plus 1 less than or equal to Bn. Okay. So you check this. Okay. So for me, I would check this one first. So this one first. And then this is second. Because if this one doesn't, if not, then the series is going to be diverged by the entrance test. Or you call the test for divergence. Okay? All right. And then we also talk about absolute convergence. So if we put the absolute value on every term, the series converge, then we call that series converge absolutely. And absolute convergence imply convergence. So if this one converge with the absolute value there, then that converge. Okay. And here are the table to give you more information. Okay. So for example, this one is useful for series that contain both positive and negative term. You want to put the absolute value there and try to prove the series with the absolute value over here converge. Okay, power series. Okay, power series. For power series, okay, then remember this result. This power series is a geometric series. It converges if and only if the absolute value of x is less than 1. And when you converge, it converges 1 over 1 minus x. Okay, and I have some comment of some convention and those. And if you try to find if a power series, if you try to find for what value of x is this power series converge, you use the ratio test, like that. Okay. Use the ratio test. So to find the interval convergence and the radius convergence, you use the ratio test. Okay. Almost always use the ratio test. And I highlight some steps over here. Step 1, 2, 3. Number 1, you find the limit of this ratio of an plus 1 over an. Okay, that should be the this one here should be okay. It's not the that should be in the index. An plus 1. Okay, an plus 1 over an, and want to see what does it go to. Okay. Now, in this case, it goes to 1/3 absolute value x plus 1. Then you will solve this, set that equal to 1, and you solve for x. And then use it as a 2 endpoint. And you know that within this 2 endpoint, it's going to converge absolutely by the ratio test. It's going to diverge outside. But then for the endpoint over here, for step 4, you want to find out what happened to the endpoint. Then you go ahead and substitute, and then use the other test to see if the series converge or diverge. And then at last, you put them together. So for example, here diverge and here diverge. We don't include any one of this endpoint. So the interval converging will be that, and the way that's converging will be 3. So that was how we use it. Okay, so here's the thing. Okay, the last part here, 11.9. Then we represent the function as power series. We remember this one. So if you can relate to this function, a function of 1 over 1 minus the quantity, you can represent this function as a power series, this power geometric series, providing the absolute value of this common ratio is less than 1 that way. So here's the example how we use it. Okay, and to find the interval convergence, you just need to solve this inequality. When you set the absolute value of the common ratio less than 1, you solve that, you find the interval convergence. And there's no need to check endpoint. Why? How come we don't need to check endpoint? Because it is a geometric series. Geometric series going to converge even only if the absolute value of the common ratio is less than 1. Okay, when it's equal to 1, it's going to be divergent. So when it's equal to 1, that's at the endpoint, then the series diverge. So there's no way, there's no need to check endpoint. We know it's going to diverge anyway. Okay. Okay, here's some example of how to represent, for example, like this function. So kind of try to relate to 1 over 1 minus a quantity. Okay, and then you continue. Okay, and then express that in a power series like that. Okay, and then this one over here, we try to find a power series representation of this one. You should try to relate that with this a function of this form. This time you had to actually differentiate. You see that the derivative that is this. So antiderivative this, you will get back to this. So you will write the power series for this function and then integrate term by term to get back to the function that you're interested in. And then when you do that, so you will integrate term by term of the power series. And you need to figure out what this constant C here is. To figure out this constant C, you plug in the center of this power series. In this case, is the center of that is 0. So plug in x equal to 0. You try to, and then you can figure out what this C here is equal to. And then once this equals 0, then this will be the power series representation of this function, providing that is within the interval convergence. Okay. All right. So that's the end.